Okay, guys, today we're going to talk about earthquakes. So, in this lesson, we're going to figure out what causes earthquakes and how we measure both their distance and their epicenter and the magnitude of them. So, first, what causes earthquakes? Earthquakes are plates that are in constant motion and interacting along boundaries. These motions of boundaries create strong forces that act on rock. To a certain extent, rocks can bend and stretch. This is known as elastic deformation. However, as that stress continues to build, the elastic deformation is overcome and faults form. So as the rocks move past each other at faults, the surfaces catch, creating more stress. Once the elastic deformation is reached, the rocks break past each other, releasing large amounts of energy. As a result, an earthquake happens and it releases three different seismic waves. The first wave is a primary wave, also known as a P wave. This causes rocks to move back and forth in the same direction as the wave is traveling. It's a compression wave. And these waves can actually travel through the solid iron core. It moves often like you would think a slinky, where it compresses and then pulls apart. The secondary wave, or an S wave, moves at the right angle to the direction of motion. So it goes up and down like an ocean wave. These cannot go through the core. And then the last wave is a surface wave. These rock in a backward motion and a side-to-side motion. And the particles move at a 90-degree angle of motion to the direction of movement. Surface waves are the ones that cause the most damage in an earthquake. So where do earthquakes occur? Well, you have two different terms. You have focus and epicenter. The focus is the point in the Earth where the earthquake's energy originates within the Earth's surface. So the focus is down here on the fault line. They're usually within the first 65 kilometers of the surface, and the seismic waves move out from there in a rippling effect. The epicenter is the town or area directly above the focus. So when an earthquake occurs, the three seismic waves are sent out throughout the Earth. The primary wave moves the fastest and are registered first on a seismograph. The secondary wave arrives second. The difference between the two waves' arrival times tells you how far you are away from the epicenter of the earthquake. The further you are, the longer it takes the secondary wave to hit you. So for instance, let's think about two cars. We have a very fast car, sports car, and we'll say a Ferrari, going against a Honda. So if we were to drive that car from here to the intermediate school, they would get there in about the same amount of time. There wouldn't be a real big lag time between the time that the Ferrari comes to the intermediate school to the time that the Honda does. But if we take those two cars and we race them from the middle school to New York City, there's going to be a much bigger difference in the time in which when the Ferrari gets to you to when the secondary wave or the Honda would get to you, because it's a much further distance that they're traveling. So here we look at earthquake data. There's a lot of information on this graph. So first you see here we have the primary wave arrival time. So that's always times 0. It's when we start our stopwatch. We're like, oh, okay, our Ferrari has arrived. That's the primary wave. And now we sit there and we wait. And we wait for the time for the Honda to come, which would be your secondary wave. The further you are away, the longer the time it's going to take for that to get to you. At that point, we know our interval. That's known as an S&P interval, which is right here. So the time between the primary wave arriving, which is always times 0, and the secondary wave arriving is the S&P interval. And you subtract the secondary wave, which is the second one, from the primary wave. Well, here you look at this time, minus 0 gives you your S&P interval. The other thing on here is amplitude, which is the height of the secondary wave, which we'll get to in a few moments. So once you have your S&P interval, you can determine how far away you are from the epicenter. For instance, if we go back to the first slide, we can look here, this is times 0, and we look, each of these blue lines is worth 2. So here's 30, 32, 34, 36. And if I follow that line down from here, you'll see it's 36 seconds. Okay? So now you look at the epicenter graph, the distance graph, and you go up to 36, seconds. So each of these is worth 1. So the black line's worth is 35. So you go up 1 more to 36. And you follow that across to the slope of the line, because it's a linear relationship, and then follow it down. Okay, so, and then each of these is worth, the bottom axis is worth 20. So 320, 340, 360, and it's between the two, so it's 350 kilometers. Now that's a radius in any direction. That doesn't tell us if it's coming from the north, the south, the east, or the west. So the earthquake could have been the Atlantic Ocean, it could have been in New York City, it could have been down in Virginia, or it could have been up in Canada. We don't know exactly where it was, we just know it was 350 kilometers in a radius in any direction. So you need to use 3 different sites in order to figure out your epicenter. The reason for this is because it is a circle. So here, if we look at this earthquake that happened in Japan, you have this yellow circle. So we know that the earthquake epicenter happened somewhere in here. So I'm thinking that the seismograph was probably in Tokyo, and Tokyo is reading it outward in a circle. So then you have to also look at another location. Let's take the green circle, for instance, and they also make a circle. Well, any 2 circles, when you overlap them, will intersect in 2 points. So here and somewhere over here. So we take a third location and you end up doing that one, and any 3 circles that intersect will intersect at 1 point. So here, the epicenter was somewhere around Kobe or Osaka. So now we know how to get the epicenter of an earthquake. Now we need to figure out how big was it. Was it a 4.0 magnitude or a 9.2 magnitude? To figure out how much energy was released during the earthquake, you now need to look at that maximum amplitude of the secondary wave. So here's your primary wave, remember at time 0. Your secondary wave is where that second wave big peak starts, and now you're looking at how high up, the highest amplitude. The amplitude can you either measure from the top or the bottom. It's the same thing, but you always want to measure it from 0 upward, and the axes are the same. So now you look at the amplitude here, you find the highest point, follow it across on the blue line, and each of these is worth 10. So 150, 160, 170, 180, 190. So that's 190 millimeters of amplitude. So now how does that amplitude convert to a magnitude? You look at the Richter's magnitude scale, and you're going to use your distance and your amplitude to figure out your magnitude. So for instance, we look at the distance, and you will do these more in class tomorrow. So you look at your distance, 400, we'll say this one was 420, and the amplitude for this was 190, so it crosses over this magnitude line. Then you do 2 other sites, because remember from previously we had 3 sites to figure out our epicenter. You also need 3 sites in order to figure out a good representation of your magnitude. So now the blue line shows here, you have, goes across, it's 500, and probably about 90, so it crosses over. And then you have your green line at 710 and 30, and they all cross over somewhere around 6.7. The more points you have, the better the accuracy. So in here, each of these is worth 0.1. So 6.0, 6.1, this is 6.5, 6.6, so it's around 6.7 is the magnitude. So now what I'm going to have you guys do is go back through and look at the PowerPoint and your notes, and to answer your WSQ questions, and then also get ready for class tomorrow. Make sure you come up with 1 question on your WISC. I will see you tomorrow in class. Good night.